Hi, everyone. What we're going to be learning about today are infinite sequences and limits. So, an infinite sequence is basically a sequence that can go on forever and ever, or at least in theory, it can. And when we talk about a limit, we're going to talk about if that sequence was to go on forever, what is it approaching? Is it approaching a particular number? Is it going to infinity? Is it going to zero? Is it going to two? So that's what we would be calculating when we're trying to calculate the limit. So I have an example for you here, and the example is with a fractal. Now, a fractal is formed by starting with what we call the seed and applying a rule over and over again to whatever we get as a result. So we start with a seed, we apply a rule, we get something. Then we apply the rule to what we got. And then we apply the rule to the result of that. And we do that over and over again. So geometric sequence, arithmetic sequence, we did the same thing. We started with something and we did apply a rule over and over again. So this particular example that I have for you is called the Sierpinski triangle. It's a very well-known fractal. And the way it is formed is we start with a triangle, we connect the midpoints of the triangle, and we remove the middle of the triangle. And we do that over and over again. So let's go ahead and let's apply this. Hold on, I have to find my pen here. Okay, so when we start with this triangle, we're going to say that this triangle right here has an area of 1. If you notice, when we connect midpoint to midpoint to midpoint, we've actually created 1, 2, 3, 4 equally sized triangles. So when we remove one of them, we are left with 3/4 of the previous, which is just 3/4. Okay, so the area that remains is 3/4. I know that's messy, but you know what it says. Then what we do is we apply the rule again to the 3 triangles that remain. So we go midpoint to midpoint to midpoint on all 3 triangles and we cut out that middle piece. And what we're left with is 3 out of 4 of all of the triangles that were there. So we're left with 3/4 of the original 3/4. I'm just going to rewrite that as 3/4 squared. And then guess what? We do that again. Now it's getting too small for me to write, but you can see each of these little triangles, we connect, 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 and then remove the middle. So what we have is 3/4 of the previous. So 3/4 of 3/4 squared is 3/4 to the third power. And that's the area of the little black triangles that all remain. And then guess what? We do it again. So now all these little baby triangles, we do it again, and we're left with 3/4 of the previous area. So we're left with 3/4 to the fourth power. And it got too small, so I didn't even include the next one. But if we took all these little bits here and we connected midpoint to midpoint to midpoint and removed the middle, what we would be left out of what we originally started with would be 3/4 to the fifth power. Now, I want you to think about this. If we keep removing pieces of this triangle away, the area that remains is less and less and less. It's never actually going to be zero, though, because we're always going to be taking 3/4 of some amount, even if the triangles were barely there, little tiny crumbs. 3/4 of something is still something. So I want you to notice we have in the first iteration, that's what we call it, the application of the rule, our area was 3/4. The second time we applied the rule, the area was 3/4 squared. The third time, 3/4 cubed. Fourth time, 3/4 to the fourths. So if we did this x times, we would have an area of 3/4 to the x power. All right. So we know some things. I do want to graph this, so I want you to take a look. When we graph this, we would need the area in terms of decimals. So I'm going to give you those decimals. Okay, so write these down. And then I want you to graph them on that little grid that I gave you, because I want you to have a visual of what's happening to the area. We already talked about that the area is getting smaller and smaller and smaller, but I want you to see how that happens. So hopefully you're graphing your points right now. 3.42. And if we continued at the 6th iteration, it would be just under 0.2. At the 7th iteration, it would be just above 0.1. 8th iteration, and they start dropping slower and slower and slower, but they're still dropping. So look what happens to our area. Try to do this neatly. And here's the thing. It's never going to actually reach zero, but it is approaching zero. So what we say, and this is super, super important right here, this is super important. We say that the limit as x approaches infinity, so in other words, as x gets bigger and bigger and bigger, as we keep applying this rule, and the rule was 3/4 to the x, well, the limit is zero. And again, what that means is if we keep applying this rule over and over and over again, we're going to get really close to zero. Even though we're not going to actually get there, we're getting really close to that. Okay. So let's look at this example. And I wrote down some numbers for you here. I'm going to move this. So what if we wanted to estimate the limit of this particular sequence? This is the rule. That's kind of a messy rule. So one way that we could do it, which we really don't want to use this way, is just to drop numbers in that get bigger and bigger and bigger. So I picked 3 numbers. I said, well, what if n was 10? What if n was 100? And what if n was 1,000? What would this value be? And the values went from 0.2 to 0.02 to 0.002. And what that tells me is that the limits are decreasing. Over and over and over again, they're decreasing. They'll never be negative. They'll never be zero, but they're going to approach zero. So again, we would say something like this. The limit as n in this case approaches infinity of 2n squared minus 1 over n cubed plus 1 is 0. So I'm going to say 2 things. First of all, not every limit approaches 0. It's just a coincidence that these two both approach 0. The second thing is, this is not a method we want to have to use. We don't want to have to guess and check and drop numbers in. So we actually have a way to do this, okay? And we can use some rules, and we can apply some rules. So we have many theorems for limits. And I want you to take a look at these, okay? And we're going to talk about them, and it's going to really make sense when we use them. So first of all, when we take a limit of 2 values that are being added together, and again, the limit is always going to be as the numbers are getting bigger. So as n approaches infinity, and you see that on all of these. We can actually take the limit of each term individually and then add those limits together. Same thing goes for subtraction. Same thing goes for multiplication and division. Okay, so we can take individual limits of different terms and then apply whatever if it's multiplication or division, whatever the operation is. If we were to take the limit of a constant, in other words, like the limit of 5, think about a line at a height of 5. It doesn't matter if x is 1 billion. The height is still 5. So if we take the limit of a constant, it's just going to be whatever that constant is, whatever that number is. Okay, so how does this work? What do we do? What does this all look like? So we're going to do some problems. And I'm going to give you a method that you're going to have to follow. Super, super important for you to understand how to do this. Now, I'm going to be honest. On the next page, I'm going to show you a shortcut. But the shortcut is going to kind of be like, you read the end of the book, but you still have to read the whole book. So you have to show me how you got to this. So I'd like to start with this third example. We're trying to take the limit of this fraction. And of course, n is approaching infinity. Here's what we're going to do. We're going to take the variable with the biggest exponent from our denominator. So in this case, it happens to be n squared. And we are going to divide every single term in the numerator and denominator by n squared. So here's what we do. We say 2n cubed divided by n squared plus 8n divided by n squared plus 15 divided by n squared. And then we also do it to the denominator, so 3n squared divided by n squared plus 1 divided by n squared. And now what we can do is we can simplify. Let's see what we can do here. So n cubed over n squared, well, I can simplify that, so it's just 2n to the first. The second fraction, the 8, nothing's going to happen to the 8, but the n in the numerator and one of the n's in the denominator will cancel each other out. 15 over n squared, I can't simplify that. Here I have n squared over n squared. Those just cancel each other out, so I'm left with the 3. And 1 over n squared cannot be simplified. Okay, so we have all these fractions, and we have to think about what their value would be as n approaches infinity. So in other words, as n gets bigger and bigger and bigger, what happens? Going for another color. It's so important that you see this. Let's go for red. So if we have 2 times the number n, and n keeps getting bigger and bigger and bigger and bigger and bigger, this will approach infinity, because that value will just keep getting bigger and bigger and bigger and bigger and bigger. So it grows without bound. The second fraction, we have 8 divided by n. So I want you to think about this. If we had 8 divided by 1, it's 8. 8 divided by 2 is 4. 8 divided by 8 is 1. 8 divided by bigger and bigger numbers, actually the value of this fraction becomes smaller and smaller and smaller and smaller and smaller. And it's never going to be negative, but it's going to eventually become a value that's pretty close to 0. Think about if it was 8 over 1 million, 8 over 1 billion. So that fraction would approach 0. In fact, the same thing would happen here because, again, as n squared is getting bigger and bigger and bigger, so as n's getting bigger, then we square it. We're going to have 15 over larger and larger and larger numbers, so this fraction would approach 0. In our denominator, well, 3 is just 3. We've already canceled out those n's, so there's nothing we can do there. And 1 over n squared, again, same routine as the top. When we have that variable in the denominator, this fraction is essentially going to become 0 or approach 0. So let's look at what we have here. Infinity plus 0, which is infinity, divided by, well, 3 plus 0 is 3. So as this number gets bigger and bigger and bigger and bigger and bigger, even though we're dividing by 3, it's still going to approach infinity. And because it's approaching infinity, what that means is there is no limit. And what we say is the limit, and if you've watched Mean Girls, you know this, the limit does not exist. Because the number grows without bound, it's going to keep increasing forever and ever and ever. So you just did a limit. You just took a limit, your first one ever. Now let's go ahead and let's look at the previous two problems. So we'll just work backwards. We'll go to this one. We're going to do the same thing. We're going to take the biggest variable, the variable with the largest exponent in the denominator, which there's only one variable there, and we're going to divide every term by that value. So n squared divided by n cubed minus 3n divided by n cubed plus 4 divided by n cubed, all divided by n cubed divided by n cubed. All right, start your reducing. Get a different color. I always like to do it in a different color. Well, n cubed divided by n cubed, that all reduces out and it just becomes 1. N squared over n cubed, this reduces to 1, and then we have an n in the denominator. N over n cubed, this would become 3 over n squared, and there's nothing we can do here. So let's see what we have. We have 1 over n, and n's getting bigger and bigger and bigger. So when that variable is in the denominator, this all approaches 0. I'm going to write it right on top. That all approaches 0. And here again, we have 3 over a really big number, right? N's getting bigger and bigger and bigger, so that approaches 0. And guess what? 4 over n cubed, that approaches 0. So look what we have, 0 over 1. 0 over 1 is 0. So the limit of this is 0, meaning if we were to graph this, it would approach 0. Not too bad, right? Let's go ahead. Let's do the next one. So the next one says 3n over n. So we're going to divide everything by n. 3n over n plus 6 over n divided by n over n. And let's start our reducing. So these will cancel each other out. So we're left with 3. This down here will reduce to 1. And we can't do anything with the 6 over n. So let's see what we have here. 3 is just 3. 6 over n, we know that one by now. When the variable's in the denominator, it approaches 0 and 1. So we are left with 3 over 1, which is just 3. So if we were to put this in the calculator and graph it, it would approach a height of 3. So notice we got a number, we got 0, and we got the limit does not exist because it approaches infinity. So 3 different scenarios. So there's a little bit of a shortcut, and that's going to be on the next page. Now again, you have to know how to do this, but I'm going to show you the shortcut right now. So if the degree of the numerator is bigger than the degree of the denominator, then the limit does not exist. Well, let's go back here for a second. If the degree in the numerator is bigger than the degree in the denominator, the limit does not exist. That's exactly what happened here. If the degree of the numerator is less than the degree in the denominator, then the limit will approach 0. The limit will equal 0. The limit of the degree of the numerator is less than the degree of the denominator. Look what we got. We got 0. Okay, scrolling again. If the degree of the numerator is equal to the degree of the denominator, then the limit will be the ratio of the lead coefficients. Lead coefficient of the numerator is 3. Lead coefficient of the denominator is 1. These degrees are equal. The limit is 3. It actually works. The shortcut works. But here's the deal. You can know that shortcut and you should know that shortcut, but you must show this work. You must show this work if you want to get full credit. Okay, this is an important thing to be able to do for calculus. So you need to practice it. Okay. The last little bit of notes that I'm going to give you today, this has to do with calculating the sum of an infinite geometric series. So now I want you to think about this. If your sequence is increasing, you're not going to be able to find the sum because the numbers that are next for each term are going to be bigger and bigger and bigger. So how can you calculate the sum? It would go to infinity. You wouldn't be able to calculate it. So this rule will only apply when the common ratio, the absolute value of the common ratio, is less than 1. And the formula will be a very simple S equals A sub 1 over 1 minus R. Okay? And we're going to practice that in class. But again, it's really important for you to know before you can actually try to start calculating the sum of an infinite geometric series, you have to decide, is the R value bigger than 1? If the R value is bigger than 1, boom, can't do it. Okay, you're not going to be able to calculate the sum. If it's less than 1, you'll be able to calculate the sum if the absolute value is less than 1. Okay, have a great day, everybody.